Imagine an object with twice the mass of our Sun. Now compress it into a sphere the size of a city, about 20 kilometers across. It spins up to 700 times per second. Its magnetic field is 1 trillion times stronger than Earth's. Its surface gravity is 200 billion times stronger than what you feel right now. A single teaspoon of its material would weigh 10 million tons. This isn't science fiction. This is a neutron star, and it's one of the most extreme objects the universe has ever produced. In our last video, we watched massive stars die in catastrophic supernovas. Today, we're looking at what those explosions leave behind. Get ready, because neutron stars and pulsars are stranger than anything we've covered so far. Born from the ashes of a supernova, when a massive star, between roughly 8 and 20 solar masses, exhausts its fuel and collapses, the outer layers explode outward in a supernova. But the core doesn't explode, it implodes. Under the crushing force of gravity, protons and electrons in the core are forced together, merging into neutrons. The entire core becomes a solid ball of neutrons, a neutron star. The process takes less than a second. A core the size of Earth is compressed to the size of a city in the blink of an eye. Understanding the density, it's almost impossible to truly grasp how dense a neutron star is. Let's try a few comparisons. If you compress the entire Earth, all 6 trillion kilograms of it, down to the density of a neutron star, it would fit inside a baseball. A single sugar cube-sized chunk of neutron star material would weigh about as much as all of humanity combined. The atoms in ordinary matter are mostly empty space, electrons orbiting far from the nucleus. In a neutron star, all that space is gone. Neutrons are packed directly against each other, with almost no gap. A discovery that shocked the world. In 1967, a young PhD student named Jocelyn Bell Burnell was analyzing data from a radio telescope in Cambridge, England. She noticed something strange in the signal, a pulse of radio waves arriving with perfect clockwork regularity. Every 33 seconds, exactly. The signal was so precise, so regular, that her team initially nicknamed the source LGM-1 for Little Green Men. They genuinely considered whether it might be an alien transmission. It wasn't. It was something far more extraordinary, the first pulsar ever discovered. How a pulsar works. A pulsar is a neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the neutron star spins, these beams sweep through space like a lighthouse. If Earth happens to be in the path of that beam, we detect a pulse every time it sweeps past us. Hence the name, pulsating star, pulsar. What makes pulsars so remarkable is their precision. They spin with such regularity that some pulsars keep time more accurately than atomic clocks. Astronomers actually use them as cosmic reference points, natural GPS beacons spread across the galaxy. Millisecond pulsars, the fastest spinners. Some pulsars spin incredibly fast, hundreds of times per second. These are called millisecond pulsars. They form when a neutron star in a binary system steals material from its companion, spinning up like a top being wound tighter and tighter. The fastest known pulsar spins 716 times per second. Its surface is moving at about 24% of the speed of light. If a millisecond pulsar were the size of a basketball, a point on its equator would be traveling at roughly 70,000 kilometers per second, fast enough to circle Earth 5 times every second. Neutron stars turned up to 11. Not all neutron stars are calm, ticking pulsars. Some are born with magnetic fields so extreme they belong in a different category entirely. These are called magnetars. A magnetar's magnetic field is roughly 1,000 times stronger than a typical neutron star, and 1 trillion times stronger than Earth's magnetic field. These fields are so powerful they can distort the very shape of atoms. Electrons near a magnetar are stretched into thin tubes aligned with the magnetic field lines. Occasionally, the crust of a magnetar cracks under the stress of its own magnetic field, causing a starquake. The energy released in milliseconds can exceed what our Sun emits in 100,000 years. In 2004, a magnetar 50,000 light-years away released a burst of energy so powerful that, despite the distance, it partially ionized Earth's upper atmosphere from 50,000 light-years away. If a magnetar were located where the nearest star system is, just 4 light-years away, its magnetic field alone would be lethal to life on Earth. The closest known magnetar is about 9,000 light-years away. We're perfectly safe, the most metal event in the universe. Sometimes, 2 neutron stars end up orbiting each other in a binary system. Over millions of years, they emit gravitational waves, ripples in space-time, losing energy with each orbit, spiraling closer and closer together, until finally they collide. The result is called a kilonova, an explosion roughly 1,000 times more powerful than a standard nova. The collision either forms a more massive neutron star or collapses directly into a black hole. But here's the extraordinary part. Neutron star mergers are now believed to be the primary source of the heaviest elements in the universe. Gold, platinum, silver, uranium, all of it, forged in the collision of two neutron stars. In 2017, astronomers detected gravitational waves from a neutron star merger for the very first time and followed up with telescopes to watch the kilonova unfold in real time. They observed the spectral signature of freshly forged gold and strontium in the explosion. In that single event, an amount of gold roughly equal to several times the mass of Earth was created in seconds. The gold in your ring, your watch, your phone. It came from a collision like this one, billions of years ago, somewhere in the galaxy. Neutron stars exist right at the edge of possibility. They are the most extreme objects that can exist without collapsing into a black hole. There's a maximum mass a neutron star can hold, estimated at around 2 to 3 solar masses. Beyond that, not even the pressure between neutrons is strong enough to resist gravity. The star collapses further, past the point of no return, and becomes a black hole. Neutron stars and black holes are cosmic neighbors on the spectrum of extreme, and the line between them is razor thin. In 2019, LIGO detected a gravitational wave signal from a merger involving an object in the mass gap between neutron stars and black holes, too heavy to be a neutron star, possibly too light to be a black hole. Astronomers still aren't sure what it was. The universe, as always, doesn't like to make things easy for us. Neutron stars are what happens when the universe pushes matter to its absolute limits and stops just short of creating a black hole. They spin like tops, pulse like beacons, quake like planets, and collide to forge the heaviest elements in existence. They were discovered by accident, mistaken for alien signals, and have since become some of the most scientifically valuable objects in the sky. And they remind us that even in the aftermath of destruction, the universe finds a way to create something extraordinary. In the next video, we're going back to a star we mentioned earlier, one that might explode in our lifetime. Betelgeuse, the red supergiant that has astronomers watching the sky every single night. If this video gave you something to think about, a like and a subscribe means the world. It helps more curious people find this channel. Drop a comment. Which neutron star fact broke your brain the most today? See you in the next one. Keep looking up.